a touch, baby. I look around since city's cold and empty. No one's around to judge me. I can see clearly when you're gone. And I said, ooh, I'm blinded by the lights. No, I can't sleep until I feel your touch. I said, ooh, I'm drowning in the night. Oh, when I'm like this, you're the one I trust. Hey, hey, hey. I'm running out of time, 'cause I can see the sun light up the sky. So I hit the road in overdrive, baby. Oh, the city's cold and empty. No one's around to judge me. I can see clearly when you're gone. And I said, ooh, I'm blinded by the lights. No, I can't sleep until I feel your touch. I said, ooh, I'm drowning in the night. Oh, when I'm like this, you're the one I trust. I'm just coming back to let you know I can never say it on the phone. They'll never let you go this time. I said, ooh, I'm blinded by the lights. No, I can't sleep until I feel your touch. Hey, hey, I said, ooh, I'm blinded by the lights. No, I can't sleep until I feel your touch.
Good afternoon, everyone, and welcome to AABC's Tab Talk webinar series. My name is Colleen McCain, and I'll be moderating today's webinar. Thanks to all our members and non-members across the community for participating today, and a special thanks to Dwyer for supporting this webinar. I have a few Zoom notes before we get started. If you have questions for our speaker, please use the Q&A button in your Zoom window, not the chat, and we will feed those questions to our speaker at the conclusion of the presentation. You can submit questions using the Q&A button at any time. No need to wait until the end. If you have technical issues, please use the chat box to inform the panelists, and someone will assist you shortly. Today's session is all about the high accuracy, low cost building ventilation verification tool. And here's a little bit about our expert joining us today. Caton Mande is a senior R&D engineer at the UC Davis Western Cooling Efficiency Center with over 10 years of applied research experience with energy efficiency in buildings. His work focuses on developing advanced control systems, making high accuracy airflow measurements, and characterizing the performance of heating, ventilation, and air conditioning systems. Caton holds a Bachelor of Science from UC Davis and a Master of Science from Georgia Tech. So now I'm going to hand it off to Caton to get us started. Caton, take it away.
Thank you, Colleen. Welcome everyone again. I'm happy to be here to present on this project that we've been working on for about a year now, and to share the results and the knowledge that we've gained with you. So I'm going to talk to you about the low-cost, high-accuracy building ventilation screening tool that we've been developing with funding provided by the Office of Naval Research. Really quick, if for those of you who are not familiar with the Western Cooling Efficiency Center, I just wanted to provide you with two quick slides to show you where we are kind of oriented within the world. So our mission is to accelerate the development and commercialization of efficient heating, cooling, and energy distribution solutions through stakeholder engagement, innovation, research development, education, and outreach. We're a pretty uniquely positioned center in the sense that we kind of have a foot both in academia and industry. We are directed by Dr. Mark Madera and Dr. Vinod Narayanan, and Teresa Pistakini is our engineering manager. Our center definitely fluctuates throughout over time, but at any given point, we have about a dozen full-time engineers that are working on research projects focused on energy efficiency in buildings with funding from the California Energy Commission, California Utilities, the DOE, DOD, NASA, or any one of our corporate affiliates, at which you see the logos here. Since we do have the 1 foot in academia, we are continually assisted by graduate students that are pursuing master's or PhD degrees. So to start with a general overview of this project, I wanted to talk to you about these 3 goals that we have. So the first one is the value that we're looking to add in providing a building owner or manager with a low-cost tool to screen HVAC zones for ventilation issues. What's behind this idea is, we want to provide these building owners and managers with a new data source, one that can hopefully allow them to identify problematic areas quickly, and also with that new data, make data-driven decisions on what to do next. As we do that, we're going to be developing the ventilation screening tool prototype. This tool is going to measure zone by zone ventilation using the carbon dioxide decay method. Our goal and what we are using currently is a low cost, high accuracy off the shelf CO2 sensor. So this is not something that you would have to, license from us or build up or design yourself. And then we're also leveraging a wireless mesh network to simplify the deployment and to ensure communications as you deploy these sensors throughout a building. So as I had mentioned, this project's funded by the Office of Naval Research, and the way that this funding structure works is we got partnered with a specific entity within the DoD, where our problem statement aligned with a current issue that they are having, and we got paired up with Naval Facilities Northwest. And those, for those of you unfamiliar with it, Naval Facilities is the command that is responsible for maintaining, updating, and fixing issues that are present in the naval bases throughout the world. And if you kind of think about them, they're a pretty unique user. For Naval Facilities Northwest specifically, they're located up in Washington State, and they have buildings that they are constantly, retrofitting for new tenant improvements or maintaining that have been around since World War II. So they have quite a range of systems that they are working with, plus, buildings that have been around through many iterations of building codes. What you can see on the right here in this picture, I'll speak about it more later in the presentation, but this is just kind of an overview of the components that are currently part of this tool. So I've talked about what we're trying to do, but to give you the full context, what we're looking at is helping any testing, adjusting, or balancing contractor, or anybody that would hire a testing and adjusting and balancing contractor to bring additional data and potentially reduce the time it takes to get an initial measurement so that that new data could be used to make further decisions. So as I'm sure most of you are familiar with, testing, adjusting, and balancing is an iterative process where you measure the airflow in buildings and go around and adjust dampers and other components to make sure that the HVAC system is operating as designed and you're getting the required airflows in the different zones. So this is conducted by a certified contractor and inspector. There's a very standard methodology. All the tools used in this are certified by a very rigorous process. And one of the main applications of this is confirming that when you're working in commercial spaces, that you're getting ventilation flow to meet the design specification in the occupied areas. So we're not looking to displace anything that is currently being used, but what we're looking at right now is a way to add additional value within this testing phase, to make some of that information that is currently unavailable to building owners or managers more readily available to help improve decisions. So I wanted to just highlight some of the currently available tools, which I assume most of you are very familiar with. I kind of break these into two different categories when I think about this. I break it into categories on whether or not the tool itself is measuring the velocity of the air or the actual volume of the air. So when we're talking about velocity, we're talking about something like a hot wire anemometer or a pitot tube, where you need to get direct access to the airstream that you're measuring, whether that is a predetermined spot, whether by a pitot tube being installed during construction, or ports that have been pre-trilled for taking a continuous commissioning type measurement. You need to get access to the air, and what you're truly measuring with these devices is the velocity of that air. So when we think about ventilation requirements and building design, primarily we're talking about the volume of air that's going into each space, because our rooms are three-dimensional. So when you take these velocity measurements, you do have to do additional steps to recover the actual volume measurement. So just in a general example, you can see here that this individual is taking a measurement within this duct, and to calculate the flow that is moving past that point, they would need to have the cross-sectional area. Another tool is a flow hood, and that can be seen in this upper left picture, this illustration here. This is a tool that does typically give you the volume flow rate. It is also commonly using an array of pitot tubes itself, or in some cases a hot wire anemometer. But the tool manufacturer has already done the work for you to take that velocity measurement and convert it back to volume. So these are very useful tools, and pretty easy to use. The complication is you do need to have access to the grill to measure the flow that's coming out of the grill. So in a lot of cases, that's pretty simple, but in some buildings, it can be pretty challenging, both in terms of, whether or not the grills are relatively high off the ground, so you would need a ladder, or, as tenant improvements are being done, sometimes the location of the grills are not necessarily considered, and they can end up in a location that's actually very hard to access. Making it difficult to get this flow hood there to actually get that measurement. The other part is each one of the flow hoods tends to kind of have a limited range at which they are manufactured or are designed for. So, depending on the type of building that you're measuring or you're doing a testing and balancing measurement on, you potentially need different devices to be able to capture and accurately measure the range of airflows that you see within that building. So now that you have an idea of overview of what's currently going on, this gives us, or now I want to talk about kind of our approach. So our approach is based off the fact that carbon dioxide is present in the air. Typically, the outside air concentration is about 400 parts per million. And in an indoor space that's occupied to then kind of the design conditions, so the number of people that was expected within the design. And when it's being well ventilated, the concentration sits around 1,000 parts per million. So the reason that we have ventilation air in these spaces is to really dilute the concentration of CO2 and other indoor pollutants that are outputted by occupants, plus off-gassing and everything that is already within the space. But what we're really looking at is just the CO2 component of this. And within that, the difference between the CO2 within the space and the CO2 outside of the space is the signal that we're looking to use to measure the amount of CO2 actually entering the space. So I mentioned the decay method. The decay method is nothing new. It's something that's been in literature for quite some time. And it's based off of the concept that, I have a volume of air within the space. If that's at a certain CO2 concentration and I start bringing in ventilation air that's at a lower CO2 concentration, as I displace that air that was originally in the room, I capture an air change rate per hour. So if I know the volume of the room, then that converts me directly to my ventilation air flow rate. So what we're proposing here is, the simple, easy to use tool where you operate your ventilation system as designed. And just to take a quick step back, the assumption here is that some level of tab has already been done. This wouldn't be used in the very first iteration. This is more going to a building that is having complaints, or a building that doesn't have any active measurement. So it's a building that's operating, so that you can posture the system as it would be, and then take your first measurement. So you operate that ventilation system and you measure the outside air CO2. Then when the space is unoccupied, you raise the CO2 concentration, and you could potentially use the people who previously occupied the space as that. But for our testing conditions, what we do is we primarily just artificially add CO2 to the space from a CO2 cylinder and raise the concentration to something over 1,000 parts per million. And the reason for that is just it gives us a good strong signal to measure that decay. So as I'd mentioned, what the sensors are truly measuring is the air change per hour. Now this could be measured by one or more sensors within the zone. And where that comes into play is under this methodology is a well-mixed air assumption. And what's meant by that is that as I bring in the fresh outside air, that it's displacing a equal volume of room air, but that room air that was displaced was well mixed and represents the overall CO2 concentration within the room. One exciting part about this project is that by making these low-cost sensors, allowing us to add more to the room to see a little bit more of the flow distribution within a given zone. And then lastly, depending on what you want the actual answer to be in terms of units, you just need to look to measure the volume of the space to convert back and forth between the air changes per hour and the actual ventilation flow rate. So now that you have an idea of what I'm describing, I just wanted to describe how this is going to go or how we see this going in terms of testing. So as I'd mentioned, you operate the ventilation system, you deploy the sensor in each zone, you raise the CO2 if needed, and then the ventilation screening tool will calculate the air changes per hour. But the value that we truly see this adding is in the possibility of simultaneous measurement. So instead of taking a flow hood or an anemometer around to each grill within a zone and taking the measurements, summing them up, moving on to the next zone, what we're proposing is a big shift here where you deploy these sensors in, say, floor by floor. So if you take this simple diagram that I have here on the right, and if you just kind of think of each window that you see as a zone, what I'm trying to describe here is that you would take these sensors and you would deploy them in each zone. And because they can create a wireless mesh network and are able to communicate data through each other, you're able to take the measurement from a single location. So while each one of these measurements will take a certain amount of time, instead of going zone by zone, I can essentially measure all 6 zones at the same time. So leveraging the simultaneous measurement is one of the main core concepts behind this, and where we see there being value, both in terms of collecting a low-cost data source to drive further decisions, plus to get measurements on buildings that currently do not have a building management system or any insight to what is truly going on in the ventilation air. So by continuing this for this whole building, you would take those 6 sensors that you have, you would move them to the next zones, take that measurement, move them to the next zones, take that measurement again, and then finally you're done. So instead of having to potentially lug ladders and multiple flow hoods around, you have these small sensors that you deploy in the space, you run the system, you add CO2 if needed, and then you take the measurement. So overall, we're hoping that it'll help reduce test time. So now that I've motivated that, where are we? So what you can see on this slide is what we're calling the alpha hardware prototype. It's a pretty simple device. It has really 4 components here. We have a absolute pressure sensor, our CO2 sensor, our long range antenna, and our power supply. So the reason that we have both a pressure sensor and a CO2 sensor is the CO2 sensor we're using right now is based off of infrared scatter. And those are susceptible to pressure changes. So the sensor that we selected has the ability to connect to an external pressure sensor, which they can then use to modify its measurement. So with these 4 components right now, we are powering all these devices via USB, just because it simplifies our current test process. But the real indication here is that since we're powering it's very low power, it would be very easy to transition to something that is operated by a battery, making this application even more flexible. So, based off this picture, you can see that we've gone through our component selection and our initial testing. And right now, we're still kind of in the ongoing prototype fabrication and lab testing phase. Sorry, that should actually say lab and field testing. So we've built and tested our sensor packs. We actually at this point have over 10, and we've tested to ensure that the wireless mesh networking is working as expected. And one of the final big components of this is kind of the software side of it. So we've completed our initial web-based user interface, and we're working with our project sponsors at NAVFAC to continually iterate on that to make this a more useful tool for them. So to date, we've tested within our laboratory, and then we also have a very strong relationship with our campus energy manager at UC Davis. And we've been testing within various buildings on campus, and we'll continue to do so for the rest of the project. So let's talk about some results. So within our laboratory, we have a pretty simple single zone chamber that we've built where we have outdoor ventilation air, we have a mixing box, we have a fan controlled by a VFD, and a pressure relief damper. So this single zone system was built primarily to test DCV systems, but we've been using this in this project as well because it provides very accurate ventilation flow rates and allows us to assess both our sensors and our analysis methodologies in a controlled environment. What you can see here in this chart is just one example that I wanted to provide for you guys. So this orange line is the actual ventilation rate being provided to this space. And this is, on the high side of ventilation rates, we're at about 3.25 air changes per hour. But the exciting result here is the blue line is showing our sensors and a real-time calculation methodology that we were testing. And it's looking at the real data stream and trying to calculate what the air change per hour is. And you can see that within about 4 to 5 minutes, our methodology and sensors had converged to the actual underlying air change rate per hour. So, going back to the pitot tubes and the anemometers and the flow hoods that I talked about, this 4 to 5 minutes is, probably on the long side compared to some of the results that you can get with those tools. Maybe not so much if you're doing a true like grid traverse, but at least if you're just kind of doing like a spot measurement, you can definitely get an answer with one of those tools in a little bit shorter period of time. But the way to think about this is, since we are talking about simultaneous measurement and kind of the parallelization of this testing process, this 4 to 5 minutes doesn't stack. This 4 to 5 minutes would be used by all of the sensors. So, if you go back to the building example, if you're measuring 6 zones, you can still measure 6 zones. If they were, as represented this testing chamber, you could do all of that within 4 to 5 minutes of actual test time. But this doesn't truly represent what's going on in actual buildings. So this is definitely more the ideal case. And what we are seeing in the field is that, to get the actual measurement, it's probably more 10 to 20 minutes, but still the same thing. Once you start taking the measurement, you're taking the measurement anywhere that you have the sensors, so that if you can increase your productivity that way. So next, I was going to talk to you through some of our field results. And I wanted to start with these charts because they also kind of give you a general overview of how each one of these tests works. So in COVID times, we had the opportunity to use this tool to test a couple meeting rooms on campus. Each one of these meeting rooms had a dedicated air handler unit. Both of these rooms were old enough that there was no active monitoring on them. And basically we were approached because the occupants were interested to know how many people that they could safely put into those spaces to still work within the current COVID protocols at the time. So we went in, and as you can see, there's kind of 3 different phases to these tests. Setup time, where we're deploying our sensors and potentially placing the CO2 tanks in locations for injection. The ventilation system is running during both of these tests the whole time, so nothing equipment wise is turning on and off. So you can see we're raising the CO2 concentration, and then we shut this off, and this decay is showing us the ventilation air that is coming into the space, and it's the window that we're taking the measurement. So we learned a couple things from this test. One, the mixing within the room is not as quick as we would have expected in the beginning. So as you're adding CO2, the signal that you see is definitely noisy, and this is kind of an area of interest for the remaining part of our project. But this was also a pretty successful result because we were able to show that both of these rooms were getting over 1,000 CFM of ventilation air, and they had originally only been putting or allowing about 4 to 6 people in there for meetings. So we were able to confirm those ventilation rates and give them more confidence to allow the number of occupants to increase. Another building that we tested on campus is a office space, and this one is served by a VRF system with DOAS. And you can see the kind of the general floor plan here in the upper left. And I would say this is a fairly typical office building on campus in terms of, the outer perimeter has individual offices with open workspaces in the middle, small conference room, closet, and other open workspace. So because this is a VRF system, all of the ducting that you see is just providing the ventilation air, and those ducts are connected to a DOAS system that also has an energy recovery heat exchanger in it, so that system is both pushing and pulling air from this space. So we went in and deployed our sensors on the east side of this building as we were monitoring the outside air ventilation, as the system was operating as intended, and the building was unoccupied. And we got the following measurements. where we could see that one of the rooms was very, very close to its design ventilation requirement. Both the conference room was on the low side, but then we had this big imbalance between the 1208 and the 1207 room. So this is the 3 and 4 here. So, with this test, we were proving a couple things. One, that we could take the simultaneous measurement. So we measured from all 4 of these spaces within the building at the same time. Because this is an open space, one thing that is potentially within these numbers is calculating some air movement from other spaces. But again, the story that I'm trying to tell here is that we're looking at this to be, a screening tool, where you go into places that you either want to confirm or take an initial measurement and just get an initial data point of where are we now. So with these results, you can see that we have one room that is fine, and then the other 3, there's the potential to investigate further results or and do additional measurements. So the final result that I wanted to propose was another use case that we this isn't within the intended use, but this was something else that we did to, because it allowed us another data point to collect. So we had a different project that was going on where we were replacing a baseline unitary system with a 100% outdoor air system. And we took the ventilation screening tool there and used it to essentially measure the outside air fraction. And since these are single zones provided by unitary systems, the ventilation rate and the outdoor air fraction are the same thing. This was also one of the easiest to do a direct comparison with a flow hood. And what you can see here is for the baseline system, the ventilation screening tool was within 20% of the flow hood measurement. And when it was the 100% outside air system, it's within about 10%. So even in these 2 other applications, it's still working as designed and providing useful information about how much ventilation air is actually entering that space, not just the volume of air. So you don't have to assume that the outside air is being well mixed or well distributed throughout the space. So one of the big parts of this was, that it's low cost and accurate. So what does it cost? So right now, from that picture that we were showing, there's kind of the 4 main components. You have the pressure sensor, the CO2 sensor. There is a microcontroller and connectors components, as well as the antenna. So we're using off-the-shelf components, and right now we've been paying about $110 for each one of these sensors. While that is still potentially on the high side in terms of hardware, the thing to remember here is that, if this was actually in a true manufacturing line, you could take advantage of contracts and things like bulk discounts. So the simplicity of it, we truly think that the total hardware cost, you could drive this down by probably 50% at least. Other things that would have to be considered would obviously be the cost of assembly, and then the cost associated with any training or support or marketing that someone would provide for this tool. The final piece that I'd wanted to cover is to give you an idea of what our web-based user interface looks like. As I had mentioned, this is the most recent part of the project that we've been working on. And we've gone through 1 design iteration with NavFac already. But we're really trying to make this as simple and easy to use as possible. So what you can see here right now is the information that we would provide to the user. You have a measurement progress bar. What you don't see here is as you connect sensors, they would be listed here. So if you were doing a very small single zone system, you might just have 4 sensors. But if you're trying to do a very large multi-zone system, let's just say you have 20, they would all be listed right here. and their real-time data would be read out. Another very useful component that we have in here is a floor plan reference. Right now, the way that this is built, you have to upload a schematic. So this could be like an actual from the building plans, or you could just draw a very simple wire schematic, save it as an image file and upload it here. Eventually, we are hoping that you could potentially draw it within here, but that's kind of a nice to have feature. But once you upload the floor plan, the sensors that are listed on the right-hand side, each one of them have a tag that you can then move within the floor plan. So you have the ability to, distribute the sensors and then have a reference for where each one of those are in the space that you're measuring. And then finally, we have a real-time graph that's showing you what is being measured. Currently, everything that we're doing is still just kind of watching the CO2 concentration. So one thing that we're looking to do is find a more kind of realistic representation of that. Because while we're building this and designing and testing it, since that's the underlying signal, that's kind of what we're used to looking at. But as this goes out and becomes a tool, not everyone necessarily thinks of it that way. So in general, just kind of think of this as a real-time readout that would give you some visual indication if one sensor was reading something completely wrong or something like that. Just giving the user more overall information about what was going on with the current test without trying to overload them. This, as I had said, is kind of the second iteration. So as we continue to work with NavFac, I assume that this will continue to be updated. And we may add some features and we may remove some features. So I've kind of told you everything that we've done and where we're at and some of the results, but our project isn't over yet. We still have about 6 to 7 months left with how we're working. So in that, we're going to continue to iterate the design. This is open to both hardware and software. I don't really expect the hardware to change much. But again, as we get feedback, there is the potential that we may need to tweak something here and there. I do see the user interface being the thing that gets tweaked the most over the next 7 months. And just to make that as user-friendly and easy to use as possible. We are slated to test on about 2 or 3 more buildings on the UC Davis campus. And we'll fit that within that time. We are currently in the process of identifying buildings within the NavFac Northwest building stock for us to travel up there and demonstrate the tool for them and let them use it. And then finally, we're looking to engage with other stakeholders and share results, which is a big motivation for originally trying to share these results at the CX Energy conference and now through this webinar. So with that, that's pretty much all I have for today. So at this point, let's just open it up and to the Q&A.
Great, thank you so much, Caton. We do have some great questions lined up here for you. So I'm just going to go ahead and get started. First question is, this sounds like a DCV system. If I have a DCV system, could I use those CO2 sensors to measure the ventilation air?
Thanks, Colleen. And thank you, whoever asked that question. So at a high level, yes, this does kind of seem like it has the components to a DCV system, because you have a carbon dioxide sensor within the space. And instead of using kind of the rising CO2 signal throughout the day to determine your damper position, kind of the question, I'm interpreting the question to be, could you use that same CO2 sensor to watch the decay at the end of the day if you left the ventilation system running? And could you do the same thing that this tool would do? And overall, yes, at a high level, it is doing a very similar thing. but the difference is, or kind of a couple big differences is one, in those DCV controls, you kind of only have one CO2 sensor that is located in one position throughout the room. So if you're pretty confident that you have well-mixed air, then it wouldn't make a difference. But if you don't think the air distribution is that good, then having the ability to place more sensors throughout the space gives you more confidence in that measurement. So I hope that answers the question.
Thank you. All right, next question. How do you increase CO2 in a zone? Does it have to be a calibrated amount of CO2?
It doesn't need to be a calibrated amount. What it really depends on is how the kind of the range of the CO2 sensor. So we tend to work with CO2 sensors that kind of have a general working range of 0 to probably 10,000 parts per million. But there's obviously no need to go that high because the outside air is at about 400. So from my personal anecdotal experience, you really want to double or triple. And I guess I'll say triple to quadruple the outside air concentration, just so that you have a good strong signal. So the way that you would do that, you don't need to use a calibrated gas. You can just use, standard industrial grade CO2. And the one thing to be careful of if you are just carrying a CO2 cylinder around the space is to make sure that you're still following proper safety precautions for ensuring that it's not going to fall over and damage the tank or the valve or anything like that. So right now, the standard procedure would be to start adding CO2 and then watch sensors that are near where the injection is. And when you get around that, triple or more, you would turn off the injection, let the room mix a little bit, and then you watch the decay.
Okay. Next question. Is this method a way to optimize the amount of outside air coming into the spaces? Then it can be controlled to meet a certain reading?
So that's going to be my interpretation of that's very similar to the DCV question. So this, if I didn't mention it clearly enough, this is meant to be like a temporary deployment of sensors. Just like you're not going to leave your flow hood attached to a register for an extended period of time. These wireless CO2 sensors that I talked about, you would deploy them within a space temporarily, take the measurement and remove them. So at this point, they would not be used for any other type of control. And I hope that answers that question good enough.
Great, thanks. Next question. Are you thinking that the screening tool will replace a current tool on the market?
So our idea right now is not that it's going to replace a tool or that it would even, really change any part of the tab process. Our main hope for this is that it, because you can do the simultaneous measurement, and because the goal is to make the tool, easy to use, that we open up the opportunity for more non-subject matter experts to collect high quality data that then can be used to drive further decisions. So to give that more details, like with NavFac, since they have buildings that have been around since before or around World War II, they have a section of their building stock that obviously has no building management system, was built to different building codes, and they have no idea what the current status of that building is. So if someone came in and wanted to use that building and it needed tenant improvements, they don't have any current information on the current baseline. So they could obviously get the building tabbed, and if the project affords for that, there's no need to change that. But in the case that they wanted to make potentially a decision of what part of the building to tab, or if only one floor or something needed to be, the hope is that this tool lowers the barrier of entry, so you can get kind of initial screening element and triage the building into spaces that currently seem okay versus ones that are definitely bad and ones that are good. And then once you have that information, then you're returning to your trusty tab contractor to get more information and more fidelity within those problem areas. But you have the confidence that you don't have to do that high fidelity measurement everywhere.
Okay, thanks. Next question. In the lab testing the sensor placed at the airflow outlet of the chamber, which helped make the test accurate, how are you accomplishing that in the field when most spaces have multiple paths of outlet, i.e. multiple return air grills?
It's a good question. So that's one place where that diagram kind of deviates from reality. So the sensors that were there, those are more the sensors that are being used to control the chamber itself, and how we know what the true underlying ventilation rate is. Those didn't represent the sensors that would be this low cost, high accuracy screening tool. So these sensors will take the measurement wherever you place them. So that's where the well mixed condition assumption kind of comes into this, because if you were confident and knew that the entire zone was well mixed, you could put the sensor anywhere and it would give you the same result. But since that doesn't necessarily hold because of airflow paths, opening and closing doors, things like that, the way to really think of it is wherever you're placing the sensor within the space, that's the air change per hour that you're measuring right there. So the hope is that if this is low cost enough, you can always deploy multiple, and we can do some type of sensor fusion to give you an average there. And the other part of it is because we're using CO2 as the signal here, and almost like the tracer of where air is going. There's no need to truly measure where the air is coming into the space or where the air is leaving the space, because what you're doing is instead of, let me say this a different way. What you're doing is because you're watching the CO2 signal, you're watching the amount of outside air that's actually coming in and diluting the space regardless of where it comes from. So some component of it could be coming through the ducting system. Another component of it could be through infiltration. So, with the tools that I described in the beginning, all of those, you are looking at the airflow path, and you are obviously concerned about what's entering the space and what's leaving the space. And, then you need to make sure that you're also capturing how much ventilation air is coming in, either through the unitary system or something like a DOAS. And you have to keep track of all of that, and do that kind of mass balance. Whereas with this tool, what you're truly doing is you're just doing it within the space, and you're doing that because the outside air is providing the dilution. So since you're truly measuring how much air is coming, the rate at which new air is coming in to dilute the room air, you're no longer as concerned about where inlets or outlets are.
Okay, next question. Can this tool still provide value if the building management system is constantly monitoring outside airflow?
That's a good question. Yes. So this wouldn't provide as much value, because you'd obviously have some idea of where outside airflow is coming in if you already had a managed system. But this would still give you the opportunity to screen it and give you another data point. So, I mean, with that, our kind of main target here has always been buildings where you don't necessarily have a building management system, or you're unsure just because maybe you have a building management system, but you don't have that sensor installed. So giving you data where there's no data, but it would be no different to give you additional data when you already have data, So hopefully if it's, low cost and easy to use, it opens up the door, for a verification measurement there, or, additional troubleshooting, stuff like that.
Okay. Next question, is this testing recommended for single zone systems only, or would this testing work in a multi-zone space that gets air from other spaces besides outside air?
It's a good question. So single zone is obviously the easiest. And that's because you have the single source of dilution. The hope of using the multiple sensors is to expand to those multi-zones. And one of those results that I showed in that VRF, each one of those rooms is technically considered its own zone from the VRF, and from the ventilation air. And as I had mentioned, some of the results were potentially influenced by air coming from those other zones. So that's definitely one part of this tool that is still under consideration. It's something that can definitely be done. The question is, the solution that I'm thinking of is it either requires some amount of trying to tag the other air that would come into those zones, or getting your sensor placement, measuring the multi-zone spaces with enough sensors that you do have an idea of where the potential non-outdoor source of air is coming from.
Okay, thanks. Only a couple more questions here. Knowing total supply air CFM in a classroom fan coil unit, can outside air and return air quantities be determined?
Can you read that one again?
Sure. Knowing total outside air CFM in a classroom fan coil unit, can outside air and return air quantities be determined?
With just that one piece of information, no. But if you do know the outside air fraction, or obviously one of those other flows, then you could determine it. But otherwise, it's an undefined system. So what I also mean there by outside air fraction is you could use CO2 in that application. So if you are able to measure the CO2 in the supply, the CO2 in the room, and the CO2 from the air, that would give you the ability to make that outside air fraction measurement, which would then allow you to recover the other two from just supply. But without something else like that, you couldn't.
Okay. Last question. Studies in the past have highlighted that large errors can be present in measuring ACR depending on the sampling position, even in a small test chamber. How many sensors per space are you using, and how are you determining where to place them?
It's a really good question. I'm going to say that I don't actually have a complete answer for it yet, because that's part of what we're trying to learn from this. So, I mean, like our current methodology is kind of focused around, like an equal distribution around the space. But, hopefully what we kind of can glean from some of these results is whether or not you need that fine of a grid, or if it should be symmetrical versus asymmetrical, or something like that. And the other part of it that I would just go with is that, this in some sense, the ultimate goal in, let's say 20 plus years, would be that this could be, a tool that you use just like you would a flow hood or an anemometer. But at this point in time, what it's really going for is just doing an initial screening. So accuracy is important, but truly there's kind of some wiggle room there, because you're just really looking to kind of triage spaces and triage your building. So you're looking kind of from a very high level to find areas that are clearly problematic. And that could fall into categories that are clearly getting no ventilation air, which would not depend too much on the sampling area, or spaces that are getting way too much ventilation air. And again, kind of the distribution within the space does not impact that a whole, or is not going to be the most sensitive variable there. So I hope that answers that question.
Thank you so much to everyone for submitting your questions for Caton. I'd like to thank Dwyer again for supporting this webinar, as well as Caton for lending us his expertise today. Thank you so much. A quick reminder, if you are an AABC certified TBE or TBT, you will receive the AIA Learning Unit Certificate to keep for your records within 24 hours to your email. But please allow 7 days for your CEU credits to be uploaded automatically to your portal. If you enjoyed this presentation, the Tab Talk webinar series continues next month with the talk on August 25th titled Air Tightness Testing for Building Enclosures with Sam Myers from RetroTech and Nathan Colley from Penn Air Control, Inc. Registration is now open on aabc.com. Thank you all for joining in for today's webinar, and thank you again, Caton and Dwyer. We hope to see you next time.
Thank you, Colleen.
Bye, everyone.